Okay, yeah, thank you. So I would like to discuss a problem in scalar curvature and how it's connected, naturally connected to the theory of quantitative operate case theory. And in the end, I would like to discuss some other applications. Okay, so let me first introduce the problem. So I know the audience is very diverse, so but I would like to make my talk accessible. So if you have any question, just let me know. Uh, so, oops, I guess this button. Oh, sorry. Oh yeah. Uh, so first, the concept of scalar curvature. This is probably the most elementary uh, concept in differential geometry. So a scalar curvature is just about like uh, locally the size or volume of a ball, say with radius r. So I start with a Riemann manifold and at a point P and compare it to the volume of the same size ball in the Euclidean space. So when I is very small, you have this asymptotic formula. Okay, so K here is the scalar curvature. So if the scalar curvature is positive, locally it means the volume of the small ball it's smaller compared to the Euclidean ball of the same size. If it's negative, then it's bigger. So it's very, very intuitive. It's probably the most intuitive curvature concept in geometry. Now, the reason it's interesting, it's related to problems in mathematical physics and in general relativity in particular. So the question I'm going to address is what kind of like topological constraint, like if the scalar curvature is positive, okay? Now, this is a very intuitive, let me try to draw a picture. It's very, everything is very intuitive. So what is a good example of like positive scalar curvature? So if you have like one manifold, say Riemann manifold X, if you cross it like just with S2, then if you like make the direction of S2, I mean, give S2 the standard Riemann metric of the sphere, but rescale it by like a small epsilon, then the curvature in S2 will dominate because the scalar curvature, it's essentially the sums of all sectional curvatures. So in this direction, the section curvature will dominate. So it will make it positive. So intuitively, oops, intuitively, let's see. So intuitively, oh, it works now. So intuitively, if the scalar curvature is positive, then locally it's this kind of vibration. So you can have some kind of vibration like locally it's there's an S2 and in some direction. So the idea is that the intuitive idea is that if you fill in the S2 direction here, and then of course the fundamental class will collapse. And that's the problem. That's the conjecture, actually. Oh, so I have this page about like possible different approaches to scalar curvature, but that's just some history. So intuitively, so if you like embed the space into a big space, and here that's such an embedding. So this is actually a universal embedding. So you embed, well, actually you can embed any metric space into this gigantic metric space. So this is a universal embedding. That's the formula. Okay, this is actually an isometric embedding. So it means this space, the L infinity, is really a black box. Anything you have, any geometric object you have, there is an isometric copy in this huge space. Okay. Now if you embed this Riemann manifold like into this huge space. And if you fill in a little bit, and if the fundamental class, well, I'm assuming this is, let me assume this is oriented. Okay, so then if you fill in, and if the fundamental class vanish, and if that's, so for an R neighborhood, and the smaller such an R is called the filling radius, okay? So it's just like in this picture, you fill in and the fundamental class collapse, okay? Now, if you have positive scalar curvature, it says, intuitively you will be able to do this. And so this is a conjecture of Gromov. And so there is like a constant which depends only on the dimension of the manifold and the scalar curvature low bound, okay, such that the filling radius is going to be less than or equal to this. Okay, it's going to be, okay. So it's a very natural, very intuitive, like conjecture, okay. And but it's a very powerful conjecture. So this actually, if true, then it implies this conjecture of Gromov, Lawson, and Zhizhang Xie. So if you have a closed aspherical manifold, then you cannot have any Riemann metric with positive scalar curvature. Okay, and the reason is that if you have such a positive scalar curvature metric on M, and if you consider the universal cover actually is going to have, of an aspherical manifold, is going to have infinite filling radius. So that's how you derive this. So this conjecture can be viewed as a quantitative statement of the Gromov, Lawson, Zhizhang Xie conjecture. Okay, so it's everything I talk about here fits very well with the philosophy of Shimo's talk. It's like it's a quantitative geometry of topology. Okay, so this is a basic problem we are going to address. So so I'm working with some colleagues, and also some two young postdocs. And so we are not able to solve this conjecture, but instead we proved like a large scale version of that. So and that's, I think, what we, so I'm going to tell you what we are able to prove, then I'm going to outline the strategy of proof. Okay, so instead of the usual like dimension of the manifold, so I'm going to replace the dimension, the usual classical dimension, by so-called asymptotic dimension. Okay, so if we make this change, then we are able to prove the conjecture of Gromov. Okay, so this is a large scale version of dimension. Okay, so the intuition is that if you have placed a geometric object, and if you travel very far away and look back, and that's the dimension you see. Okay, so it's an analog of covering dimension. So it's the smallest m such that for each r, and they exist a uniformly bounded cover. Okay, so that every ball with that radius r intersect only at most m+1 members of the cover. And so if you compare it to the classic covering dimension, the only difference it makes is, instead of a point in the covering dimension definition, now we use a ball with radius r. And this is a larger scale version because looking from very far away, you would not be able to tell like a ball of size r with a point. Okay, so that's why it's called sometimes called large scale dimension or asymptotic dimension. Okay, it's a very natural concept. Okay. So this is the result we are able to prove. It's essentially the conjecture of Gromov, but replacing the classical dimension by asymptotic dimension. Okay, and so yeah, this is a result with a postdoc. He actually was a former PhD student of mine, also another postdoc, and my colleague Zhizhang. And so let me also say, in the spirit of Shimo's talk, quantitative topology, we are able to make this constant very explicit. The constant is like, so this number, we can actually really make it precise. And it's like power, the dimension, and it's an exponential constant. I mean, the filling radius can be, okay? Now, and we don't think we have the optimal like constant, okay? But the like to find the optimal constant, it's related to a very elementary problem, which I'm going to discuss a little bit later on. Okay, so this is the result we're able to prove. Okay, but the tools are very, sorry. So let me first, I mean, it's a combination of some Dirac operate technique, but combination with some quantitative like operate case theory, which now I'm going to introduce. I think the first part, the Dirac part, is very classic. I apologize to the expert, I think. Oh, I'm assuming spin. So I kind of swept this under the rug. Yeah. Yeah. I'm assuming spin. We actually, the conjecture, so that's a technical point, but it's a very good point. So the conjecture of Gromov was formulated without the spin condition. And actually, with our approach, we don't know how to prove the same result without spin condition. That's a very good question. And I imagine you can use the minimum surface method in low dimensions and avoid the spin. But we, yeah, we don't know how. But we don't have any dimensional restriction. That's probably the advantage of this method. Okay, so here is a Dirac operator, okay, which has appeared in quite a few talks. Okay, so Dirac was interested in manufacturing an operator whose square is the Laplacian. Okay, all right. So well, he was able, I think, in Dirac's work. If you look at his book, he built this operator up to dimension 4. So up to like in dimension 2. So for example, in dimension 2 and equal to 2, you can pick these two match. It's like I negative I 0 0, and C2 is like 1 0 negative 1 0. Okay, you can make a very explicit choice, and but in high dimension, this is actually it's an elementary problem, but it's already non-trivial to if you try to write down huge matrices satisfying this non-linear relations, it's not so easy. But the way around it is you just introduce a finite dimensional algebra with those things as generators, and that's so you have those generators acts on the finite dimensional algebra by like multiplication. Of course, it's a linear transformation, and it automatically satisfies this. Okay. Nowadays it's very easy, but historically, even in dimension 4, it's like the quaternions that was a big discovery. So it's a non-trivial idea. It's the use of Clifford algebra. Now, I also swept under the rug on which Hilbert space you are acting. And it is like essentially the minimum smallest Hilbert space on which all those things can act. So there's a little bit representation theory involved. Okay, so now once you have this construction, I also should mention one important point, and which is that in order to like get this formula, we are also using this formula, which is quite important. and that's from multivariable calculus. I think this is called the Crellon's formula. A couple of years ago, when my son studied multivariable calculus, I learned the name of this. Okay, but that's like a fundamental fact we are using here. Now in general, so when you have a Riemann manifold, so we just imitate the process, except we have to replace the partial derivative by covariant derivative because we no longer have a single coordinate chart. Okay, but now with this, if we try to see the square is Laplacian, and this formula no longer holds because with covariant derivative and the difference of these two is exactly the curvature. So we expect there is an L term because this formula no longer holds. The L term should be curvature. Now, if we sit down and do a little bit calculation, and the nice thing is that it's a code of scalar curvature. Okay, so the reason curvature appears, it's not mysterious, but it's scalar curvature. That's something we have to sit down and compute. Okay, so now, of course, this wonderful formula establishes a connection between geometry and operator theory. So my background when I grew up is like operator theory. So whenever a problem is about operator theory, so I feel, oh, I can do something. Okay, so the connection is if the scalar curvature is positive, because this operator is non-negative, then it's invertible. Okay, so that's the connection. Okay, now you would think, an operator is just a linear transformation. We know how to decide a linear transformation is invertible or not, but in the finite dimension case, of course, we just compute the determinant, right? If it's non-zero, then it's invertible, otherwise it's not. But in the infinite dimensional case, we don't have such a thing as like determinant. So here we need a new invariant. Okay, so this is a purely infinite dimensional invariant, and that's the concept of Fredholm index. So Fredholm index is defined to be the dimensional kernel minus the dimensional co-kernel. Now, it's very natural to consider them the kernel and co-kernel. So the kernel is about uniqueness of the linear system. If you try to solve a linear system like this, it's the uniqueness of solution. The co-kernel is actually about like existence when such a linear system has solution. So separately, these two quantity is about uniqueness and the existence of the linear solutions of linear systems. So it's the only natural thing to consider. But the remarkable insight is to take their difference. And the reason we want to take their difference is that because each of them separately, they are very unstable. If you make a small perturbation, those things, the dimension can change. But together, they don't change. So this is very remarkable. And there are very few things in mathematics when you make a perturbation, they don't change, right? And so it is actually this very property which makes this index computable. So the general strategy when you try to compute such an index is, you make some perturbation until you have an operator for which you can literally solve the equation. So there are many different ways of proving or computing Fredholm index, but if you think about it, it all boils down to that simple point. Okay. All right. Now this Fredholm index is an abstraction to invertibility. Actually, in some sense, it's a complete invariant. So in the sense that Fredholm index is not zero if and only if up to like a small perturbation, it's invertible. Okay, so it's a complete invariant. Sorry, but it's a complete invariant only if this invariant makes sense. So we are assuming to make sense out of it, we are assuming this is finite dimensional kernel co-kernel. Okay, Now, luckily, when the manifold is compact, then it is finite dimension, so this makes sense. All right. Okay, so but in general, so the problem we are going to address, actually the problem we talked about uh, only is interesting when the manifold is non-compact. If you are studying a compact manifold, it's like the spherical manifold, you would have to look at its universal cover. Okay. All right. So the real invariant we need is the so-called high index. Okay. So what is high index? So that deals with the case the manifold is non-compact, or if you have a compact manifold, you look at its universal cover. Okay. So now we imitate the Fredholm index formula. We try to look at the co-kernel and co-kernel. All right. So, but unfortunately, in general, kernel, co-kernel are both infinite dimensional. Okay. So, and how do you measure something which is infinite dimensional? I think the first person who thought about this is John von Neumann. John von Neumann wrote a little book called The Continuous Geometry, in which he has a theory how to measure the dimension of something infinite dimensional. Okay, but his main idea is that you should measure the dimension of something which is classically infinite dimensional by using an algebra. Okay, so it's the concept of dimension is relative to an algebra. Okay, so that's why it's very much related to what Yasso was talking about. Okay, then Alan Kahn, well, actually Gelfand was also involved. They developed into into a huge machinery. Okay, so I'm lying a little bit. Actually, to define the high index, you would need not so projection is like spectrum at 0. You would need the information about spectrum near 0. Okay, so I put a quotation sign here, but that's the spirit. Okay, so now I have to introduce like an algebra, or more precisely an operator algebra, which will be used to measure the dimension of those spaces. Okay, again, this is certainly also an obstruction to invertibility. Okay, all right, so, oops. Oops. Okay, so just like in Yasso's talk, and the algebra we are interested in are called C-star algebras. And so the simplest definition, like in Yasso's talk, we start with a Hilbert space. We look at all the algebra of all bounded linear operators. It has, of course, the natural adjoint or star operation, and also it has the so-called operate norm, which measures how much you are distorting the length of a vector. So assist algebra is a sub-algebra. So this is a huge algebra close under the operate norm closure and the adjoint operation. So that's a very simple definition. Now, sometimes we view as a assist algebra as in general as a so-called non-commutative space, because Gelfand showed that any commutative assist algebra is isomorphic to C0 of X. X is a like locally compact space, and C0 just means the algebra of all continuous functions vanishing at infinity. When you take the limit go to infinity, it's 0. Okay, so this means that in spirit, studying commutative system algebras is equivalent to studying like locally compact spaces. So essentially, every problem in topology can be translated to this language. But sometimes, of course, it does not always help. But so this subject of system algebra sometimes is called non-commutative topology or geometry. Okay, so actually, to incorporate the size of scalar curvature or things like this, we need an extra structure on the system algebra. So what we call like geometric system algebra by imitating the language from geometric group theory. Okay, so it's a system algebra and with a length function on it. Okay, so every element in the system algebra, I assign a length. I allow the length to be infinity. Okay, but I want the elements with finite length to be dense in it. Otherwise, you can assign everything to be infinity, then it's of course not interesting. So this is a natural condition. But I also want to have some like sub-additivity, but only for elements in the unit ball. Well, earlier when I was working with my collaborator Avi or we don't have this condition, but then I realized that for some actually for the examples we are interested, we only have that for elements in the unit ball. Here is like a very concrete examples, an example. So just the continuous, the algebra of all continuous functions. So this is a commutative system algebra. So this is a very natural length function. So it's about regularity. It's essentially first order derivative. I want to avoid derivative because the space may not be smooth, right? So this is the length, okay? And actually this length, it fits very well with the quantitative topology Shimo was talking about yesterday. So I will explain. Okay, so this is probably the most natural length, and this is in a way already suffices to solve the problem. So this is a very basic example. I mean, it looks very elementary, but this is already essentially good enough to solve the problem on scalar curvature. So this example. Oops. Hmm? Yeah. I want them to both in the ball because otherwise, the problem is that when you compare this, you have like so this is essentially like derivative, and you use the product of the derivative. This estimate would not work. Yeah, that's the reason. Okay. Oh, that's a good point. I think we can, yeah, we can put the sum. Yeah, I can put the sum requirement. Yeah. Oh, I don't really care. No, yeah, I don't really care. Uh, yeah, but some examples you can. Well, yeah. So I think it's not even true. It's not continuous. Yeah, yeah. But we don't need this. Yeah, but it's not true actually. There is no continuity here. Okay, so this length function. So you can see it. You can see it from this example. So this is a highly non-commutative example, which also will be useful in some other problem I'm going to discuss in the end. So for any discrete group, we look at the group algebra. And so this is a very important algebra when you study topology, like what Shimo was talking about. You translate a topological problem to an algebraic problem. This is one of the most, well, sometimes you take Z coefficient, but since I'm an analyst, I would like to do it with Z coefficient. So you just take formal sum, finite sum, with complex coefficient with group elements. This is an algebra. Okay, this is a way of turning a group into an algebra, a formal sum. You can multiply it, right? Okay, so then you can, there's some natural completion. Okay, that's an algebra. Now, well, I guess there's this huge subject of geometric group theory and of studying discrete groups by looking at the geometry. So what is the geometry? You put a length function on the group. For any countable group, there's always a length function. They are all equivalent in some sense. But the most natural way is like you take, well, if the group is finitely generated, you take like a finite generating set. It defines the length of a group element to be like the minimal numbers of generators, you need to express that group element. So that's called the word length. Okay. So there are some natural magic. So if you have a length length function on the group, you can define a length on the system algebra by just taking the maximum and the maximum length of the group elements for which the coefficient is non-zero. But of course, if you do this, and this might be infinity, but the elements which are like finite is dense. So that's good enough. So that's also a typical example. Oh, here is actually another algebra we need to solve that problem. Okay, so because to measure the dimension of the kernel, things like this, and the projection, all the projection near spectrum zero can be expressed under operators like this. So if you have a Riemann manifold, you look at the outer space of the manifold, but actually, with some coefficient in the vector bundle, but I'm ignoring this because it's really just similar. So the most natural operator we can consider is a so-called kernel operator. So you have like a continuous osmosis function, if you wish, and which defines an operator like this. So the length, so you can think this as an infinite continuous matrix. And so the length, if you think this as a continuous matrix, and so you have a lot of non-zero here, it's zero. So the length is just the width of the band with non-zero entries of this continuous matrix. So that's what it is. Okay, it's very intuitive. Okay. Oops. Oh, sorry. Okay, so now this is the language we use to measure the dimension of classical infinite dimensional space. We use the projection, of course. Now, so I mean, the usual language is K-theory. K-theory is like you use the projection, the abelian group generated by all the projection. Okay, all right. But in order to include the quantitative feature of the scalar curvature, like the lower bound, things like this, we would need to take advantage of the geometric structure of the system algebra. So we introduce this so-called quantitative K-theory. So instead of using projections, because projections are very rigid, they often have infinite lengths. So we do an approximation of the projection. After approximation, we get something called quasi-projection. We can require them to be self-adjoint. That's not a major problem. But projections are things whose square is itself. Here we just have something very small. Okay. All right. So but the important thing is we have this finite band or finite length property. Okay. That R is here. The epsilon is not important. If you wish, you can fix epsilon to be 1/10 or 1/100. Okay, I'm just putting it there to make things more flexible. But if you wish, you can ignore that epsilon because you can always make the epsilon smaller. And but the cost is by making epsilon smaller, then the R will become bigger. Okay, so there's a cost of doing this. Okay, so now actually initially we introduced this so-called quantitative K-theory to compute K-theory because K-theory is hard to compute of system algebras. The reason is that unlike in classical topology for spaces, you can chop them into nice pieces. System algebras are harder to chop into pieces. So a subspace for classical spaces amounts to an ideal in a system algebra. But a lot of system algebras don't have ideals. In geometric setting, you can prove generically system algebra don't have any ideals. Actually, I would like to prove a theorem like this for general system algebra. But I asked about this question, like, can you formulate and prove a theorem for system algebra, like generically in some sense, they are like simple, meaning they don't have any ideals. I'm almost sure this is correct, but no such a theorem. But in geometric setting, like group system algebras, such a theorem is known. Okay, so now coming back to this so this is like a technical ingredient we use to show the largest scale version of Gromov's conjecture. Okay, and so it's a very elementary result. So if we have a finite dimensional simplicial complex, well, they can be non-compact. Then this is a kind of quantitative thing, like with Lipschitz control, like in Shimo's talk. So they exist not zero, which only depends on the dimension of the x, such that and K-theory, usual K-theory can be realized with K-theory with quantitative control. Okay, this is a very elementary result, and but curiously, we know how to prove this, but curiously we don't know what is optimal constant, like how it depends on the dimension. Well, we can get an estimate, which is like some constant, the power, the power, like the dimension, like c to the n with some c, but we don't know what is the optimal constant. Well, so that's a question in quantitative topology, actually, very much. Okay, so now, so let me just say, I guess with my collaborators, we wrote quite a few papers on quantitative K-theory. But the general spirit is like, well, there are two things. Like for the algebra, the kernel algebra, this is called the row algebra. Using like quantitative K-theory, you can reduce the general like computation of K-theory or quantitative K-theory to that of finite dimensional algebra. So this is a little bit like in Yasuo's talk. And finite dimensional algebra, they are matrix algebra. So, I always thought if something is finite dimensional, it's linear algebra, we can always handle. But now I changed my mind. So, okay. And but another thing I want to say is this is with Eric and Rufus. So when in a dynamic setting, when you have a group acting on a space, often it's ergodic. Ergodic would correspond to like the algebra being simple. You cannot decompose stuff into simple pieces. And but we actually the strength of this quantitative K-theory is you don't need ideals. You don't need to decompose to some spaces. There are some flexibility. You only need something like quantitative, like which is much flexible. So even if they don't have ideals, you can still decompose and compute the K-theory. So that's one of the things we did. I think so. Just to tell my story to young people. So this paper was accepted only after 6 years of refereeing, and so don't give up. Okay. Okay. So in case you're about to fall asleep, I give you a homework, but problem. But I don't know how to do this, so I raise this as an open problem. So let's see, look at the symmetric group of n elements. It's a finite group. It's a finite group. But with two generators, one is a cyclic permutation, one is just swapping 1 and 2. Okay, so you use this to create like a word length on the group. Now, of course, this algebra we know, it's like generated, the system algebra generated by this group. But with this length function, can you compute the quantitative K-theory? Okay. Now this is such a specific one. I'm sure, I think, some smart people, young people can do it. I don't know how to do it, but I did not try very hard. So and now this is just a starting point. So if you are able to do the same thing for finite groups, you would solve the Novikov conjecture for residually finite groups. So that's a big problem. Okay, so the Novikov conjecture, a lot of us worked very hard on that, but it's widely open for residually finite groups. So what I'm saying is that if you understand the finite groups for quantitative K theory, and everything is done. Okay, so this is a good problem to think about. And, okay, so you might.
You want to really be looking at something like the disjoint union of those symmetric groups, whether they're fixed or not.
I'm really doing this, but for quantitative K theory, we don't have to look at disjoint union. But it is secretly that's what we are doing, because we are fixing some, control constant. Oops. Just make sure I don't run out of time. Okay. Okay. So now this will make a connection to the quantitative K theory. So if your scalar curvature has a low bound C, positive, then not only the index, the high index vanish, but it vanishes in quantitative K theory of certain scale. So this constant depends only on the C. Okay. So I mean, previously we introduced the quantitative K theory to compute K theory, but now, this quantitative K theory, like we found out, it encodes the asymptotic, like the quantitative behavior of the scalar curvature. So it has its own interest, and not just a tool of computing K theory. Okay, so this is essentially, so once we make this connection, now we just have to understand this group. Okay, and but they are not so easy to compute, and this estimation, like, let me just go back a little bit. But luckily, this group actually has certain duality. The other group, for like just for simplicity of complexes, which is purely a topological problem, this is in principle due to this group. That has some duality. So if we understood the other group, we understand this group. It's some kind of, I think here we probably people like to talk about Miller symmetry, but this is another kind of symmetry. Okay, so we study this group via the other group, which is much more topological. That's essentially that's the strategy of the proof. Oops. Oh, this is just an outline of the proof. It essentially is what I said, but in more technical terms. So I'm not going to go through this. Okay. So this is just the proof. Okay. So that's like how scalar curvature like um, is related to quantitative operator K theory. So, okay, so now I'm going to mention some other directions which I have been working with Shimo, Jiancao, and also some other project with Rufus. Um, okay, so I'm just going to be very brief. Okay, Shimo and I have been discussing a lot. So during this conference. Okay, that's the nice thing. Okay, so this is, I think, during COVID, I think, we were all locked up in our rooms, and but it's great. We have very good friends Shimo and we would talk over Zoom. So this was one of the problem we talked. And so we were interested in finding out like quasi-representations of discrete groups. So those are finite dimensional quasi-representations. Normally, when you like discuss representation of big groups, like infinite groups on like finite dimensional space, not much interesting is going on, okay? But those are quasi-representations. They are almost respect the product up to a small constant. Now, this turns out to have a very rich structure, okay? But this fits very well with quantitative, not K-series, but K-homage. And they are in a different language. So I'm just going to give you one sample result using the idea, well, how related to quantitative. Okay, so one thing, so one question people in group theory or in computer science, they are interested in, like, how can you tell if you are given a quasi-representation, is it very close to a representation, a true representation? Okay, so that's one of the important question in the subject. Okay, so in the work with Shimo and Qiantao, we build this. Well, I just call character map. I have not gotten approval from Shimo. Like, is this a good word? Well, I only put down this word like last night or the night before last night. And so you associate like a quasi-representation of the group to a K-series, equivalent K-series class over this universal space for proper action. This can be made very precise. This looks mysterious. So it's some kind of Lip's complex. Okay, it's something very concrete. Okay. All right. So this, but this is of course the mysterious object we are trying to study. We put it in like as a vector bundle over something very concrete. And in nice situation, like for example, it's when it's amenable. Actually, the group of quasi-representation, if you, well, we are K-series people, so we whatever we study, we let it generate an abelian group. Okay, this is abelian group, and actually is isomorphic to this group. This group we know very well. And so now coming back to the question, so in particular, if two quasi-representation is equivalent, if and only if two vector bundles are equivalent. But the vector bundles, we have a lot of tools. Now, coming back to the question, whether a quasi-representation is equivalent to a true representation. And here, in the K-series, this amounts to asking if the corresponding K-series class over the universal space is equivalent to a flat bundle. And that can be effectively studied, at least rationally, via the chain character. The chain character, you can really tell. So if it's a flat bundle, after taking the chain character, the information is in zero-dimensional part. Okay, everything else vanishes. So there's essentially a very effective way of studying this. Okay, so that's one other like application to of this quantitative K-series or quantitative K-homage. So let me just also mention another, but I think, well, there was some classification people for this algebra, but they probably all left, went home. But I still, it's just, this is my last page. So Huaxing was here for breakfast, but I will show him this slide when I go to Shanghai. But anyway, so in system algebra, there's this huge industry of classifying system algebra. There's a lot of people who contributed to this. I only mention one work because that's their work is directly related to what we do. So they classified system algebra with so-called finite nuclear dimension using K-series data. But assuming if it satisfies this so-called universal coefficient theorem. So what the universal coefficient theorem just says how K-homology is related to K-theory. Okay, this became a very powerful tool in classification. So essentially, of course, if without like some nuclear condition, it's essentially impossible to classify. So this is essentially the best one can do. But now the big task is to verify the universal coefficient theorem. So this is what Rufus and I was able to do using the quantitative K-homology theory. Is we are able to prove the universal coefficient theorem, assuming the system algebra satisfies some finite. This is also some kind of finite dimensionality, but it's not the same, at least on the surface, not the same as finite nuclear dimension. Okay, but if it satisfies our finite dimensionality, then what do we call finite complexity? So then the universal coefficient theorem holds. Okay, all right. So the big open question is that if if it has the nuclear finite dimensionality, does that imply our finite complexity? So this is a very elementary problem. So, but I think this is a task of the system algebra people. I view myself as a user of system algebra. So now we feel it's your job, okay, to answer this question. So this is, well, of course, I hope, I mean, either the answer is, if the answer is yes, we are very happy. Of course, Rufus and I would be very happy. If the answer is no, I think not only we are happy, they are happy because this problem of classification is solved. Now, if it's no, we are still happy because it reveals new phenomena. So it will give us some interesting example to study. Okay, but in case you are interested in this work, this has been published in, it's a relatively long paper, so it's in the Memoir of the European Mathematical Society. So if you are interested. Okay, well, thank you very much.
Okay, thanks very much for the talk. So, is there any questions?
Yes. Could you please go back to the slide that you skipped before you switch topics and work through it?
Okay, sure. Okay, so okay, now I have to recall my. So this is not the paper is on arXiv. We submitted the paper. So I think the outline I give is not it's only spiritually the same as the proof in the paper, but I think in spirit it's along the same line. So I mean the proof is, you know, you try to look at this is essentially the index. You put this in the quantitative. This is the high index here.
So you said it's 0 in this case.
Yeah, it is 0. But if it is 0, so essentially, oh, sorry, I take back. So this is a map from, this is K-homology because it's kind of confusing. In the algebra, if it's in the up position, it's K-homology. So the way, so we want to say, well, we want to try to detect, you know, the high index. One way of doing this is, it's like particle physics, like in building a supercollider. So instead of like computing the high index directly in the K-series, we build something in the K-homology, then pair them up. If the pairing is non-zero, then you know the high index is not 0. Okay, so this was the approach it takes. Essentially, we show, yeah.
You assume positive scalar curvature, so you're assuming the index is 0 already.
Yeah, but we compute this like so if it's zero, then we computed the pairing. That's right. So the high index. So we computed the pairing with something here, and essentially it contains information about the fundamental class being put in a neighborhood of M. So if it's zero, so it's going to be, this thing will be zero. So then you estimate the filling radius from there. So yeah, so we like get part of the information of the high index by computing the pairing, and the pairing encodes the fundamental class.
So to speak, the R on the right is somehow the R in the neighborhood
Yeah,
of infinity that you,
yeah,
where the cycle is going to be.
yeah, exactly, exactly. Because this is a neighborhood. This is a neighborhood. Yeah, yeah, sure.
So this pairing is non-degenerate and takes values in which space?
Oh, this pairing, because K theory, K homology, the pairing is a number. It's a numerical number. So you get here, but it's consistent. Here it says if you do this pairing, you get just the pairing of the fundamental class. I mean, this vector bundle with this, you get the fundamental class. Yeah.
Okay. Any other questions?
Yeah.
I mean, this is all very explicit. So if I have a metric of positive scalar, suppose I have a metric of positive scalar curvature, right? This more or less gives you chain that bounds that cycle.
Yeah.
Right? So if you were to have a pair of them,
Yeah.
right? I mean, the question is, do you get? I mean, is there some relative index that some numerical relative index that comes out of this with finite asymptotic dimension?
Well, there is. Oh, that's a good question. So essentially, yes, because so these elements. So if so, in this computation, this is just K theory. This is K theory with some Lipschitz control. So on this side, what it's saying is that the pairing of high index with the K homology class is equivalent to the pairing between this like vector bundle with Lipschitz control with the Dirac K homology class. So, but this is indeed a relative. If you compute cohomologically, this is a relative index. Because if you pair the Dirac operator with a vector bundle, which is trivial, like at infinity, then it is a relative index. Yeah, it is literally on this side, it's a relative index. Yeah, you are right.
Any other questions for the speaker?
As you work on quasi-representations, have you looked at applying it to understanding spectrum of the Laplace operator on one forms and powers and covers?
Oh, that's a good question. Yeah, so
By the way, we're sort of deconstructing because we began considering it because Lubatsky during Zoom was talking to me about that every week. Okay. So that was sort of where it was coming from.
Okay, that was my guess. Thank you.
yeah, it's actually, this argument. I mean, on the surface, it has nothing to do with this, but in spirit, it's very closely related. Yeah, these two things. Yeah, I mean, on surface, the problems are like unrelated, but
If you have almost closed one forms that are co-closed, then you can use them to construct quasi-representations.
Yeah, yeah. So they one forms. I mean, so you are doing this on the cohomological level. On the K theory level, it's you know, via the chain character. I mean, so so this is of course K0, right? K0, but if you do things for K1, probably it's by the chain character, it's directly related to, you know, what you are describing. That's my.
A way of generating quasi representations.
Yeah, yeah. Actually, that's kind of interesting. Yeah. So I mean, on the first glance, you might wonder. So there's, you know, are there any interesting quasi representation of like a group? But you see, here it's very rich. So it means often there are lots of elements. With so this is like, I think by hand, I think it's more, definitely more.
Almost commuting matrices that don't almost commute.
Yeah, yeah. So of course this problem also has quite a rich history, but I'm just giving like a 5 minutes, yeah, glimpse. Yeah.
So any final questions?
Is yes, sorry. Yeah. Oh, that's exactly the question. So I mean that's because so so this theorem answers exactly your question. So it in general, so it's close to a true representation if and only if the character is equivalent to a flat bundle. But if you look at the chain character, then so there is a so-called delocalized chain character, which is a rational isomorphism. So in the cohomology level, you see it very clearly. If it's so, it's rationally, it's close to a true representation if and only if the chain character like vanish in the high dimension. So it means most quasi representations are not close to. So they have to be very very special. But this provide an algorithm for you to see whether a quasi representation is close to a representation. So that's, I think that's the nice thing about this approach. I mean, I should mention there are a long history on this problem. There are many papers. Because I'm really giving a very like 5 minutes. Yeah.
Well, by the way, once you're saying that, you should emphasize that, you know, it's stably, right? So
Oh, stably. That's true. Stably.
You have the almost representation, you might have to stabilize before you could.
Yeah. But it's an obstruction. Yeah, it's stably. So it's you have sometimes have to add some, yeah, big trivial. Yeah.
All right, great. I think that's all the time we have for questions. So let's thank the speaker again.
Thank you.